All right, now consider this. We're going to continue this ideas with planes and vectors and intersections and hopefully some angles here. Okay, we're going to consider R, which is x, y, z, which was represented by some starting point, A, x1, y1, z1, and direction u, u1, u2, u3. So this could obviously be shown by an equation. We could go x, y, z, so that's the position along your vector, is equal to x1, y1, z1, and then plus u, which is u1, u2, u3, times our parameter. Okay, so now what I'm going to do is I'm actually going to rewrite this as parametric equations. Okay, so I'm going to have x equals x1 plus u1 lambda. I'm going to have y equals y1 plus u2 lambda, and z equals z1 plus u3 lambda. Now note that this is all very general, so it should work for any starting point in any direction and then any parameter. All right. Now if I solve for lambda in each of these, so I'm going to subtract the x1 and divide by u1, then what I'm going to end up with is x minus x1 divided by u1 equals lambda. If I do it here, I'm going to have y minus y1 over u2 equals lambda. And over here, I'm going to have z minus z1 over u3 equals lambda. Now, if those are all equal to lambda, then they're all equal to each other. And so therefore, I can go x minus x1 over u1 is equal to y minus y1 over u2, and then that is equal to z minus z1 over u3. Now I just did a little bit of algebraic manipulation there, but what I've done is I've now created a new type of equation for a vector line. This is a Cartesian equation for a line that is in 3 dimensions. All right, so that's kind of cool, you know, that we've got a new way to deal with this. So what does this allow us to do? Well, let's consider a new question. Let's say that we've got two vector equations, or sorry, two Cartesian equations for lines. So we've got x minus 2 over 3 equals y equals 1 minus z. So that's one line. So this is line 1. And then we've got line 2, which is represented by x equals 2y equals z minus 3. And so these are Cartesian equations for lines, right, that go through 3-dimensional space. So let's say that we wanted to find the angle between these two. Okay, now note that this does not necessarily mean that these two vectors cross. Okay, when we find an angle between two vectors, really what we're finding is the angle of the projection of those onto each other. All right, so we can go ahead and find that. We can find the angle between L1 and L2. But what we're going to need to do first, because in order to do the angle between L1 and L2, what we want is we want to be able to use our dot product, right? Because we know that the dot product of U and V is equal to the magnitude of U, the magnitude of V, and cosine theta. All right, so now what we need for this is we actually need the directions of U and V. So I need the directions of these two lines here. So in order to do that, what I'm actually going to do is what we were just looking at. Note that if I write my Cartesian equation in this format right here, the denominators will actually be my direction vector, u1, u2, u3. So I need to rewrite this in that way. So I'm going to go ahead and do that. So we're going to say L1 equals, now x is already very nicely in that format. Now y, I'm going to need to rewrite, so I'm going to go y minus 0 over 1, which is the same thing as y. And then the 1 minus z I'm going to rewrite, and notice that it's z minus z1, so I'm going to have to go z minus 1. Now, in order to get the z in front, I'm actually going to need to divide by -1. So that means that the direction vector for L1 is 3, 1, -1, right? It's the numbers on the bottoms of the fractions. We can do a very similar thing right here for L2. So we're going to do L2, and so I'm going to start with x minus 0 over 1 equals 2y minus 0 over 1, and then equals z minus 3 over 1. Now the problem is that this is 2y, and it's just supposed to be y in my equation, so I need to divide everything by 2. So I need to rewrite it as L2 equals x minus 0 divided by 2 equals, now if I divide this one by 2, the 2 is actually going to cancel out, leaving me with y minus 0 over 1 is equal to z minus 3 over 2. So again, I now get my direction vector. So this is going to be v. This is the direction vector for L2. The direction vector is u1, u2, u3, which is 2, 1, 2. Now that I've got those, I can go ahead and do the dot product. Okay? Now, with the dot product, I know that I can get the dot product by simply doing 3, 1, -1, dot product 2, 1, 2, and then I need the magnitudes of those. So I'm going to have 3 squared, which is 9 plus 1 plus 1, so 9, 10, 11, so the square root of 11. And then I need the magnitude of v. So 2 squared is 4, plus 1 is 5, plus another 2 squared is 4. So that gives me 9, so the square root of 9. And then cosine theta. No, don't do that. Holy smokes, why is it going crazy on me? Okay, now it's upside down. Man, this thing is crazy. All right, there we go, just what it's supposed to be. And so at this point, we can finish this. We'll just go cosine of theta. Sorry about that. I'm glad we were able to get it fixed out, though. And so now we do dot product. 3 times 2 is 6, plus 1.1 is 1, and -1 times 2 is -2, equals square root of 11, square root of 9. So that gives us the square root of 99. You can simplify that if you want, but you know, it really doesn't matter because I'm going to be putting it into a calculator anyway. So 6 plus 1 is 7, minus 2 is 5, so it's going to be 5 over root 99 equals cosine theta. And so what I'm going to do at this point is I'm going to bring up my handy dandy fancy calculator here, which I know is not very fancy, but we can make it fancy. And so I'm going to go 5 divided by the square root of 99. All right, which is, that didn't work the way it was supposed to. Let's try this again. So we'll go square root of 99 that is not doing the square root of 99, is it? That is crazy. Hold on. Okay, so we're going to take 5 divided by 99. We're going to take the second root of 99, which will give us 0.5025, and then we will do the inverse cosine, which gives us 59.8. I am in degrees, so 59.8 degrees. And so theta equals 59.8 degrees. Now that's pretty cool. We were able to use the idea of this Cartesian equation to be able to find the angle of between two lines. All right, so again, that's about 10 minutes. I'm going to shut off this video and you can try one more.